Hey everyone, welcome back to Real Analysis 1. This will be lecture 6 of the course, and in this section we're going to discuss monotone sequences. So let's go ahead and jump into it. So we'll call this section 2.3, monotone sequences. All right, so in the previous section we introduced we've been discussing limit theorems, and in the prior lecture we revisited a lot of the limit theorems we're familiar with from calculus and proved some of them, but more importantly kind of introduced the methodology for proving those types of theorems. And in this section we want to continue on with our look at limits and limits of sequences by examining a special kind of sequence called a monotone sequence. And so let's go ahead and define what we mean by a monotone sequence. And I think most people will probably be familiar with the idea of a monotone sequence, but just in case, let's go ahead and define these. So we would say that a sequence A sub n is monotone, a sequence A sub n is said to be, we'll say it like this, is said to be one monotone increasing if A sub n is less than or equal to A sub n plus 1 for all n and n, for all natural numbers. We say that it's monotone decreasing if A sub n is greater than or equal to A sub n plus 1 for all natural numbers. And then we have a term for kind of both, or either or, and that's just monotone. We say that it's monotone if 1 or 2. Okay, so if it's either of those. Okay, and so you'll be familiar with monotone functions from calculus. The basic idea here is that the function, if it's monotone increasing, for example, it's either flat or moving upward. Something like this, right? So this would be monotone increasing. Okay, and so the idea with, monotone increasing and monotone decreasing should be contrasted with the idea of strictly increasing or strictly decreasing, right? So strictly increasing or decreasing, so strictly increasing / decreasing, that's a little bit different. Strictly increasing means that A sub n is less than A sub n plus 1. And strictly decreasing means that A sub n is greater than A sub n plus 1, right? Meaning that each successive term is not equal ever, either larger or, in the case of decreasing, smaller. Okay, and so this is what we mean by a monotone sequence. Okay, now monotone sequences are really interesting in analysis because, especially when you couple them with the idea of a bounded sequence. So in general, bounded sequences need not converge, right? It's very easy to think of a bounded sequence that doesn't converge. For example, an example would be like sine of n, right? Even if you use natural numbers here, sine of n is going to oscillate, right? It'll oscillate between, it'll have an upper bound of 1, and it'll have a lower bound of -1, right? So it's bounded above and below, but it doesn't ever converge. Right? And obviously, though, something like the sine function here is not a monotone sequence. It goes up for a while, it goes down for a while, it goes up for a while, it goes down for a while. Right? So when we combine the idea of a bounded sequence with a monotone sequence, then we get, out of necessity, convergence. So if a sequence, actually, let's just state the theorem. The big theorem here, well, not the big theorem, one of the big theorems. If a sub n is bounded and monotone, then a sub n converges. Right? So if the sequence is bounded and it's monotone, then it must converge. Now, if it's, so hopefully, this is probably an intuitive idea. I think this is very visually obvious when you think about what these two terms mean, bounded and monotone. Let's say it's monotone increasing and bounded above. So maybe we've got an upper bound here. Well, the sequence can only go up or straight, right? So if it can only go up or be constant, then at some point it's going to reach some level, right? And remember, it can't ever come down, so it's either going to flatten out forever, in which case it converges to whatever that value is, or it's going to increase up to some limit which it never quite reaches, right? But because it can't come back down, it must level out to a limit or approach some horizontal upper bound that it maybe never hits, right? So it's a very intuitive, and I think just keeping in mind what these two words mean, it seems like it's fairly obvious that this is true. Let's go ahead and prove this theorem. Let's prove this one. So the picture is maybe intuitively helpful, but let's go ahead and put some kind of a rigorous argument around this. So let's let a sub n be a monotone increasing sequence that is bounded above. Okay, and the argument would be very similar to a monotone decreasing sequence that is bounded below. Okay, and so obviously when we say monotone and bounded, we mean if it's a monotone increasing, it must be bounded above. If it's monotone decreasing, it must be bounded below, in order for the convergence to work, right? Okay, so we'll let a sub n be a monotone increasing sequence that is bounded above, and we're going to let E equal the set of elements in the sequence. So a sub n such that n is a natural number. Right, and so we know that E is non-empty and E is bounded above. Okay, so this is all just assumptions at this point. So let's go ahead and let A equal the supremum of E, right? So the least upper bound of the set E. So if A is the least upper bound of the set E, what we're going to show is that the limit of the sequence is A. So let A equal the supremum of E. We will show that the limit as n approaches infinity of A sub n is equal to this supremum, this least upper bound. Okay, all right. And so to do this, let's go ahead and let epsilon greater than 0 be given. Okay, now by definition of a least upper bound, A minus epsilon is not an upper, by the definition of a least upper bound, A minus epsilon can't be an upper bound, right? A minus epsilon is not an upper bound on E, right? So obviously if A minus epsilon is smaller than A, and if A minus epsilon was an upper bound on E, then A minus epsilon would be the supremum, right? So obviously A minus epsilon can't be an upper bound, right? And so if A minus epsilon is not an upper bound on E, then right? The implication there is that there exists some natural number n naught, right? So some natural number n naught such that what? Do we remember? Such that a minus epsilon is less than a sub n naught, whichever term that happens to be in the sequence, which we know is less than or equal to the supremum of the set E. Right? And you can kind of think of it visually like this, right? So you've got your A up here, which is the supremum. And then you've got your a sub n naught here, and somewhere further back is a minus epsilon, right? And then somewhere above this is a sub n naught plus 1. And right, so this whole distance here, that's epsilon. Okay. And then naturally this, you would have further below that, maybe you'd have your a sub n naught minus 1, right? So these are the terms in the sequence here that I've drawn with a dot. And all we've said is that, hey, give me an epsilon greater than 0. And if once you give me that, I can find an n naught such that a minus epsilon is between successive terms of the sequence. Okay. All right. So that's the idea so far. And then what we can say is that because the sequence a sub n is monotone increasing, right? Because this is monotone increasing, we have a minus epsilon is less than a sub n, which is less than or equal to a, right? And this is going to be true for all n greater than or equal to n naught, right? Right? Think of this drawing right here. Here's n naught. Every term in the sequence that's larger, that has a larger index than n naught, is going to be larger than a minus epsilon and less than or equal to the supremum, right? That's kind of the structure we've constructed, right? Okay, well, right, given that, then a sub n is going to be in the epsilon neighborhood of a for all n greater than or equal to this n naught, right? And this is just the definition of convergence. This is the definition of convergence, right? Right. So the limit as n approaches infinity of a sub n must equal a. Okay. So I mean, it is very intuitively obvious, and it's also fairly easy to prove. You just gotta kind of remember some of these moves, epsilon neighborhoods and such. Okay. So any monotone and bounded sequence is convergent automatically. All right. Okay. Very good. Very good. Okay, and a quick corollary of this, which doesn't seem like it should be much of a corollary at first glance, is what's referred to as the so-called nested intervals property. Okay, so it's kind of a corollary. It really follows pretty quickly. This is called the nested intervals property. Okay, and here's what it says. If I sub n is a sequence of closed and bounded intervals, so closed and bounded intervals with I sub n, right, so the nth interval, having as a subset the n plus 1 interval, and this is true for all n, then the intersection of these intervals is non-empty. Okay. All right, so So if you've got a sequence of closed and bounded intervals and they're all nested, successively nested, then the intersection must not be empty. Let's take a look at a picture here. This is really easy to visualize if you draw it. I mean, when you write it out, it may not be as clear. But let's think about an interval like this. I've got A1, B1. So this would be interval 1. And then inside of that interval, I have another one, A2, B2, right? And so on. Okay. Okay, and so where this would be I sub n plus 1, this would be I sub n, and so on. I sub 1 would be the whole thing that I've drawn here, right? So these are all nested, right? And it doesn't have to be symmetrically nested like this. We'll see an example after the proof of the theorem that where, you know, one of the endpoints is fixed and the other side just kind of comes down. All right, but this is all we mean. And so what this says is that if these intervals are all nested like this and they're closed, right, and you don't have, you know, one of the outside interval can't be like infinite, right? It has to actually have a real valued endpoint. Then this intersection of all of these is necessarily, it must contain something. Okay, so it's non-empty. Okay, and I like this theorem. I really like the proof of this theorem. I think it's very clever. Let's see what that proof looks like. Let's see what it looks like here. So let's let I sub n equal the interval a sub n to b sub n. So just exactly what we've drawn above here, where a sub n and b sub n are real numbers. Okay, and we'll say, just to clarify here, a sub n must be less than or equal to b sub n. Okay. Okay, so let's start with just kind of defining what we mean by an interval. Then, because we have the I sub n is going to contain the interval with a larger index, we'll just call it I sub n plus m. This doesn't have to be, they don't have to be successive necessarily. So I sub n plus m is contained in I sub n, and this is going to be for all m greater than or equal to 0. Because of this, right? Because of this, we have a sub n is less than or equal to a sub n plus m, okay, which is less than or equal to b sub n plus m, which must be less than or equal to b sub m. Okay, now, okay, hold on now. What's all this? Well, let's draw a little picture here. Right, so on the one hand, we've got a sub n, right, and we know that a sub n plus m, because it has a larger index, must be to the right of a sub n, right? So that means a sub n is less than or equal to a sub n plus m. And then b sub n plus m would be the endpoint, the right-hand endpoint of this interval, the n plus m interval. So it's over here somewhere, right? Right, and then b sub m, so b sub m is a smaller index, so it's going to be to the right of this one, right? So you have this. Okay, right, so we've got this. If we have this nested interval situation, then this is necessarily true. Okay, all right, and so what does that mean? Well, m, if you just look at this, m could be 1, so this is basically implying that the A sequence is monotone increasing and bounded above by basically all of these B's. So A sub n is monotone increasing and bounded above And you know, if you say, well, what's it bounded above by? Well, it's bounded above by any one of these B's. It's bounded above by every BM. I'll put every BI, not to be confused, okay? So every right-hand bound of the interval is going to bound A sub n. Okay, so A sub n is monotone increase and bounded above by every BI, and so that implies that A sub n converges, right? So the main push in this theorem, the reason it's kind of thought of as a corollary, is that you get this from the previous theorem. Okay, right? So we now know that A sub n converges. Okay. Okay, and so if A sub n converges, we'll say that the limit as n approaches infinity of A sub n is equal to A for some A, right? For some A that's less than or equal to all of the B sub m's, right? And this is going to be for all m in n. Okay. Right? And so this is just, again, just like all of the implications that you receive from the fact that it's monotone increasing and that it's bounded above, right? So there exists some limit, and that limit must be less than all of the less than or equal to all of the values of the B of the right-hand endpoints, right? Because of the nested property. Okay. So what does that mean? Well, what that means, if you think about it for a moment, is that that means that whatever A happens to be, it must be in all of these intervals. Right? It must be in all of these intervals. Obviously, A is greater than or equal to all of the A sub n's, and we can see here also that A must be less than or equal to all of the B sub m's. So that means A must be in every one of these intervals, since the intervals are all nested, right? So if A is in every interval, then that is all we need. So A must be in the intersection. Okay. And so that means the intersection is not empty. Okay. Right, and you could, similar to the previous theorem, you could prove this theorem in the other direction as well, right? By using the B series of endpoints, of right-hand endpoints, and recognize, showing that that sequence is monotone decreasing. Okay. All right. Let's take a look at an example of the nested intervals theorem here. Nested intervals property. Here's a nice example. So actually, let's start by looking at, what I want to look at here is, because a subtle part of the theorem is the fact that the intervals are closed, right? I mean, it does explicitly state that, but it's not like a major sticking point in the proof. Well, it does matter, obviously, but the fact that they're all closed is absolutely imperative, right? Because what happens if the intervals are not closed? What happens if the intervals are not closed? Does it work? Let's take an example. Let's look at a counterexample where it doesn't work, where it kind of falls apart. Let's let I sub n equal the open interval 0 and 1 over n, right? And so where n is a natural number, right? So this is the natural numbers, right? And so you'll have the nested property here. If you think about this, you'll have 0. The first interval will be 0 to 1, 1 over 1, and that's going to contain the next interval, which would be 0 to 1/2, which will contain the next interval from 0 to 1/3, right? And so on. Right, and so they're all going to be nested in this way, right? But the intersection is actually empty. Right? Really, the right endpoint 0 of all of these intervals is really the only real candidate for being in the intersection. But and just by based on the fact that it's the only thing that you would ever think could be in every set, right? Because obviously this right hand endpoint is just going to shrink down until it's very, very close to 0, right? But the fact that the interval is closed, or sorry, that the interval is not closed, means that 0, while it's the only one that could even possibly be in all of these, is actually in none of them, right? So 0, the left-hand endpoint, is not in any of the intervals, right? And obviously anything else is going to eventually fall out of the intervals, right? And so for this reason, you have nested intervals, but you have an empty intersection. But if you were to change this, right? If you were to change how the intervals are defined and you make them like this instead, then the intersection here is definitely going to be 0. Right? It's just going to contain that one point 0. Right? And so the fact that the intervals are open matters for the nested intervals property. Okay, very good. Very good. Let's take a look at some more examples. We'll just kind of cruise through some fun and kind of cool examples, right? And so this example is going to be an example that exploits the main theorem, the bounded and monotone theorem, the first theorem, and not necessarily the nested intervals theorem. Right, so let's define a sequence here. Let's let a sub 1 equal 1, and for all n greater than or equal to 1, we're going to set, for all n greater than 1, strictly greater than 1, we're going to set a sub n plus 1. I'm sorry, one second. Let me write this right. Let me write this differently. No, it is, I'm sorry. So we're going to let a sub 1 equal 1, and for all n greater than or equal to 1, we set a sub n plus 1 equal to the square root of 2 times a sub n. Okay, and this sequence will converge. Okay, so this sequence will converge. Okay, this sequence will converge. And what we can do here is we can show that the sequence a sub n is monotone increasing and bounded above. And the implication will be that it converges. Okay. And what we'll end up showing here is that 1 is less than or equal to a sub n, which is less than a sub n plus 1, which is less than 2, right? And so what we'll show is that the limit actually is 2. So this sequence actually converges to 2. Let's show this. Right, so the first thing we'll do is we'll start by showing that it's monotone increasing and bounded above. Right, and what we're going to do is we're going to use like an induction argument. We'll use induction to show that a sub n is monotone increasing and bounded above. Okay, so let's start with n equals 1. Right, because remember when we construct induction arguments, we usually start with a base case, and then we assume that that property holds, and we show that it implies we assume that that property holds for the first n elements of the sequence, and we show that that implies that it's true for the n plus 1 element of the sequence. Okay, so when n is equal to 1, what do we have? Well, we've got 1 is less than or equal to a sub 1, which is defined to be 1 up here, right? Sorry, right here. A sub 1 is equal to 1. So when n is equal to 1, 1 is less than or equal to 1, which is definitely less than the square root of, well, it's less than a2, which is equal to the square root of 2 times 1, which of course we know is just the square root of 2. And we know that that's less than 2. Okay, so that's what happens when n equals 1. And we could do n equals 2, and we could do n equals 3, and we would see that this is true. It continues to be true. So let's assume this holds for all n less than or equal to k. Right? So we'll assume this holds for all n less than or equal to k. Then 1 would be less than or equal to a sub k plus 1, which will be equal to the square root of 2 times a sub k, right? And this is going to be less than a sub k plus 2, which would be equal to the square root of 2 times the previous term, a sub k plus 1, right? Okay. Right, and so a sub k plus 2 is equal to the square root of 2 times a sub k plus 1, which will be less than the square root of 4, which is equal to 2. Now, why is this? Where does this come from? Why is this? Well, let's break this term down. This is kind of the step where we actually prove the thing, right? We're going to use the induction hypothesis, and we'll kind of step forward into this case and see that it must hold everywhere. Okay, so what is a sub k plus 2? Well, it's defined to be the square root of 2 times a sub k plus 1. Okay, and we can think of that also as the square root of 2, and then a times a sub k plus 1, which is the square root of 2 times a sub k. Right, so this piece here can be stepped back. Okay. And so this we can think of as, let's break this up a little bit. There's different ways to kind of look at this and develop the inequality. So I'm just going to write it like this so we can look at each of these separately. You may not have to do it this way. Okay, so it looks like this, right? That's just the way you kind of break up these radicals. Now notice, right? Notice that, you know, of course, the first piece, the square root of 2, that's just equal to the square root of 2. And the square root of the square root of 2, right? That's just equal to the square root of the square root of 2. Okay, so we don't have to worry about those two pieces. What about this one? What about that one? Well, the square root of the square root of a sub k. Well, we know that a sub k is less than the square root, is less than 2, right? By induction, by the previous pieces, right? So this thing here must be less than the square root of the square root. Now a sub k is less than 2, so the square root of the square root of that must be less than the square root of the square root of 2, right? Right. So this is kind of a think about this piece here. Okay, and I'm going to actually bring that forward here, right? So the square root of 2 times the square root of the square root of 2 times the square root of the square root of a sub k. This must be less than the square root of 2 times the square root of the square root of 2 times the square root of the square root of 2. Right, specifically this one here and that one here. Right, we know that the square root of a sub k is less than the square root of the square root of 2 by induction. Okay, so if we just recombine these things, what do we get? Well, you've got the square root of 2, and then you've got the square root of the square root of 2 times the square root of 2, which the square root of 2 times the square root of 2 is just the square root of 2. Well, sorry, the square root of 2 times the square root of 2 is 2, and that's all in the square root, so you have the square root of 2 times the square root of 2, right? And so this is just equal to 2. Okay, and so what we've shown here is that a sub k plus 2 must be less than 2 also. Okay, and so that's the step, right? And so for all n in n, 1 is less than or equal to a sub n, which is less than a sub n plus 1, which we've just shown is less than 2, right? So that implies, so this right here is monotone increasing and bounded. This part here tells you that it's monotone increasing, and this tells you that it's bounded, right? And so by the previous theorem, the previous theorem, not the nested intervals property, but by the previous theorem, the sequence a sub n must converge. Okay. All right, and so then what is the limit here? Well, actually we can figure out what the limit, we can show that the limit is 2 pretty easily. Let's let a equal the limit as n approaches infinity of a sub n, right? So if that's the case, then a is equal to the limit as n approaches infinity of a sub n plus 1, which we would say is equal to the limit as n approaches infinity of the square root of 2 times a sub n. Okay, and that's equal to what? Well, that's equal to the square root of 2 times a. Right, and so what we see here is that this line of argument implies that a is equal to the square root of 2a. Right, and that of course implies that a squared is equal to 2a. And you can just kind of look at this and see, oh, indeed, that implies that a is equal to 2. Okay, and so the limit of this very strange kind of sequence must be 2. Okay. Right, so I like that theorem, or it's not a theorem, I like that example. I like that example a lot. I think it's got a very, I think this is an interesting chain of just an interesting inequality. Okay, let's do one more example, and then we'll call it good with this section. This is an example that explores, that uses the previous theorem, bounded monotone sequence, to explore the sequence that results in Euler's number. Right, so remember Euler's number. This is E, right? Right, so it turns out that E is equal to the limit as n approaches infinity of 1 plus 1 over n to the nth power. And so this is approximately 2.718. Okay, so this is a transcendental number that that you may be familiar with, and this this sequence here, the limit of this sequence is E. Okay, so we're going to show what we're going to do is we're going to walk through a derivation of how it is that this sequence is monotone increasing, this guy here, and bounded above, right? So we'll show that 1 plus 1 over n all to the nth power, that sequence is monotone increasing and bounded above, and the implication being that it has a limit. Okay, we won't necessarily get all the way to the finish line of how to show that that limit exists, but we can show that there must be one. Okay, so kind of similar to the previous section, we're going to start by looking at the binomial theorem. So by the binomial theorem, by the binomial theorem, we have, and we're going to call it T sub n, right? T sub n is equal to 1 plus 1 over n to the nth power, right? So, and that is equal to, let's remember the binomial theorem says that's equal to k equals 0 to n of n choose k, and then you take whatever this term is and you successively raise it to the k power. So in this case, it's 1 over n to the k power. And so let's write this thing out. So take a second and make sure you can, expand this. So it'd be 1 plus, and then n choose, well, so n choose 0 is just 1, and then n choose 1 would be n times 1 over n to the first power, and then the second term would be n times n minus 1 over 1 times 2 to the 1 over n squared power, plus, and then you could go on like this, right? And then ultimately you would get to n times n minus 1 times 1 all over n factorial, 1 times 2 dot 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 n, and this would be all raised to the 1 over n to the n power, right? Oh, sorry, so this would be 1 over n raised to the n power, right? So this would be the binomial, this would be the expansion of this guy here. Okay, and so remember, this is the nth term of a sequence T sub n. Okay, so T sub n. Right, we're considering this sequence T sub n. Okay, where T sub n is equal to this 1 plus 1 over n to the nth power. Okay. That's probably was obvious, but I think I might have failed to introduce that, but that's the idea here, right? So let's just expand this nth term of the sequence, okay, using the binomial theorem. All right, and when we do that, we get this guy. Okay. Next, let's see. So for this, okay, so what do we have here? Then for, we'll say for k equals 1 to up to n, the k plus 1 term, right? So the last term of the sum, or sorry, the k plus 1 term of the sum is, well, whatever k happens to be, it's going to look like this: n times n minus 1 dot 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 times n minus k plus 1 all over k factorial, right? And then times what? 1 over n to the k power, right? So this is the k plus first term of the sum. And what we want to do is we want to kind of take this term and expand it. We've got to do some algebra to it. Okay, and so this term here is equal to, and I'm going to rewrite this a little bit. I'm going to pull the factorial out front. Okay, and then here what I'd have is n times n minus 1 dot 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 times n minus k plus 1, all of that over n to the k, right? So basically just kind of shuffled this piece out and brought this guy here in. Okay, and I can break this product up, again, just kind of leaving this alone out here. I can break this up into n over n, right? I've got k n's in the bottom, and I've got k terms up top, right? So I can have n over n times, and then n minus 1 over n, and then n minus 2 over n would be there, right? All the way up to this last term, which is n minus k plus 1, and that would also be over n. Okay, so just kind of breaking the numerator and the denominator up, right? These are just fractions. I can multiply them together like this. Right, and so I've got 1 divided by k factorial. Now instead of writing it like this, right, this is just 1, so I'm going to like omit that one. But instead of writing n minus 1 over n, I'm going to write 1 minus 1 over n. Right, and instead of writing n minus 2 over n, I'm going to write 1 minus 2 over n, like this. All right, this will just make what we're about to do easier to look at. And then for this last one, I would write 1 minus k minus 1 over n. Okay. All right, so let me switch pages here. Okay, so we've got this piece. All right, so what have I shown so far? Well, what I've shown is that then the k plus first term of the binomial expansion of t sub n is, right, it's equal to this thing here, 1 divided by k factorial, and then it's 1 minus 1 over n, and it's 1 minus 2 over n, dot, 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 1 minus k minus 1 over n. Okay? Okay. All right, so we've got this thing. Right, and so this is one of the terms of the t sub n expansion. Right, and remember, t sub n is one of the terms in the sequence, the original sequence. So this is just one term of the binomial expansion of t sub n, right? It's just one of the terms of the binomial expansion of t sub n. So let's think about the binomial expansion of t sub n plus 1 and look at the same term. So we can similarly look at the k plus first term of the binomial expansion of t sub n plus 1. Now, I encourage you to do basically the exact same exercise, just start with the binomial expansion of what t sub n plus 1 would look like. Now remember, this is going to be 1 plus 1 over n plus 1 to the n plus 1. Okay, and so just keep that in mind, that that's what the t sub n plus 1 term looks like, and do the binomial expansion on that. And what you will find is that the k plus first term looks like this. So it looks like, it's the same exact argument as what we just went through. It literally looks like 1 over 1 times 2 dot 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 k, right? So k factorial out front, and now each of these terms is instead 1 minus 1 over 1, or n plus 1, and then 1 minus 2 over n plus 1, dot, 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 and then 1 minus k minus 1 over n plus 1. So it looks very similar, right? So these two are very similar. Here you basically got 1 minus k minus 1 over n, and here you've got 1 minus k minus 1 over n plus 1. Okay. Okay. Right. Okay, and so let's kind of put these guys next to each other and see what this looks like. Okay, so I've got 1 over 1 times 2 dot 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 times k, and then 1 minus 1 over n, 1 minus 2 over n, dot dot dot, 1 minus k minus 1 over n. Okay, and then this is for the k plus first term of t sub n. The k plus first term of t sub n plus 1 looks real similar. It's going to be 1 divided by 1 times 2 dot 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 times k, and then instead of 1 minus 1 over n, it's 1 minus 1 over n plus 1, and then 1 minus 2 over n plus 1, and then 1 minus k minus 1 over n plus 1, right? So it looks like this. Okay, now what's the relationship between these two? What's the relationship between these guys? Well, this is the k plus first term of t sub n. This is the k plus first term of t sub n plus 1. Well, it turns out that this is going to be less than this. Okay. Now you may say, how do I know that that's less? Well, these two are equal. What about these two? What happens here? How does 1 minus 1 over n compare to 1 minus 1 over n plus 1? Well, it's less than, isn't it? Right? Now think about it like this. This is 1, and you're taking away some value from it. 1 minus something smaller than 1. And here you're starting with 1 and subtracting something smaller also. Now, of the two things you subtract, which one is larger? This one. This guy here is bigger than this guy here. You're subtracting both of them from 1. That means you're subtracting more from this one than you are from this one, right? And so you get this relationship. Right? So every term of t sub n is less than every term of t sub n plus 1. Okay? And so that means t sub n is less than t sub n plus 1. For all that, right? And so if that's the case, then we're starting to see how this is a monotone sequence. Okay. Now, remember the original. We have to go back to the original expression for the rest of the picture here, though. So recall the original expression. Okay, what did it say? It said t sub n is equal to 1 plus n times 1 over n plus n minus 1 over 1 times 2 times 1 over n squared. Right, this is the binomial expansion, plus dot 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 plus n times n minus 1 dot 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 all the way to 1, and then 1 times 2 dot 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 up to n, and this would be 1 over n to the n. Okay. Okay, and so what we can do here is we can say t sub n is less than or equal to 1 plus 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus dot 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 plus 1 over 1 times 2 times 3 dot 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 n. Okay, this is just a term-by-term comparison, right? So this, we've got a less than or equal to here. Here we've got a less than. Here we've got a less than. Here we've got a less than, right? Right. So this is less than this. This is less than that, right? And so on. So on down the expression, right? And ultimately, you've got the same thing here. Okay. And so this is less than or equal to, this is going to be less than or equal to 1 plus 1 plus 1/2 plus 1 over 2 squared plus dot 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 plus 1 over 2 to the n minus 1. Okay, right? And what is this? Well, you can think of this as 1 plus 1 over 2 to the first power plus 1 over 2 squared plus dot 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 plus 1 over 2 to the n minus 1. And this is a familiar series here that we've seen. You may recall this from calculus. But this is the series, you could basically say this is 1 plus 1 minus 1/2 to the n power over 1 minus 1/2, right? And that is going to be less than 1 plus 1 over 1 minus 1/2, right? And you can just do the arithmetic here. That's going to be equal to 1 plus 1 over 1/2, which is equal to 1 plus, that's basically 2, which is 3. Okay, now where did this come from? What am I doing here? Well, just remember that this is basically this guy, if you recall, 1 plus r plus dot 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 plus r to the n minus 1. That series is equal to 1 minus r to the n over 1 minus r, and that's only really true when r is not equal to 1. So But you may recall that that's definitely something that you could pick up in calculus. But basically what we've shown with the previous page, we showed that t sub n is less than t sub n plus 1 for all n, right? And then in this most recent argument shows that t sub n is less than 3, less than or equal to 3 for all n. So t sub n equals 1 plus 1 over n to the nth power is monotone increasing and bounded above by 3. Okay, so it's bounded above by 3. And so by, the theorem from the onset of the lecture, so that the implication is that 1 plus 1 over n to the n converges, right? And it converges to something less than or equal to 3. Okay. Now, it turns out that 1 plus 1 over n, as I said at the onset, turns out that converges to the Euler number, which is approximately 2.71828, I think. There's a couple. Obviously, it goes on forever, but so I think that is the so again, we're not proving what that limit is, but you can see that the fact that a limit exists is clear from the fact that this sequence here is monotone increasing and bounded. Okay. All right, very good. Very good. So that was it's kind of a fun example, a little tricky. Make sure that you follow all of those pieces, and obviously pause the video, back it up, make sure that those all make sense to you. Now, before we leave, I wanted to find one thing. I wanted to find an infinite limit. So let's let a sub n be a sequence of real numbers Okay, so we say that a sub n, the sequence, approaches infinity. It approaches infinity, or we could say it diverges to infinity. Right, diverges to infinity if and then here's kind of how you would technically think about this. If for all m, I want to use capital M here. Sorry, let me start that. So if for all m real numbers, right, positive real numbers in this case, for all m in the positive real numbers, there exists n naught, natural number, such that a sub n is greater than m for all n greater than or equal to n naught. Right, and so the idea here is, what if you give me a bound? If you give me a real number, a large real number, m. So if you give me m, then if the sequence does approach infinity or diverge to infinity, if you give me an m, no matter how big it is, I can go find some natural number such that every term of the sequence beyond that natural number is larger than your m, right? So think of it like this. I've got a sequence, diverges to infinity. If you give me this m, all I got to do is give you this term of the sequence, and then everything beyond it is larger than m. If you give me a larger m, then I got to give you this guy in the sequence and say, okay, everything beyond that is larger than your m, right? And so it's really kind of the same idea as instead of all of the terms of the sequence squishing down and approaching an infinitesimally small region, they just keep going in one direction. Okay. Okay, so kind of as a consequence, and just to wrap up the monotone sequence section, it is the case that every monotone sequence either converges to a real number or what? Diverges to infinity. Right? If you've got a sequence and all it does is something like this, right? Go straight. If it can only level off or increase, then it must either converge, right? If it's bounded, it'll converge. If it's not bounded, then it must diverge, right? And then in either case, right? In either case, the limit as n approaches infinity of a sub n is going to be equal to whatever that least upper bound of these terms happens to be. Right, so whatever the supremum or the least upper bound of the sequence is, that's going to be the limit. Okay. All right. Very good. I think that's where we'll end it. Next time we'll continue on. We're going to start talking so sequences. You can't believe how interesting they can get. Right, so we've just started to kind of scratch the surface of sequences. Next time we'll get into something even deeper, and that's the idea of subsequences. And we'll also introduce the very, very interesting Bolzano-Weierstrass theorem. Right, so we'll look at subsequences and the Bolzano-Weierstrass theorem in the next lecture. Until then, take care.